Hello, in this video, we're going to be talking about implicit differentiation. And let's start with a couple of examples. If y equals x squared, what is the value of dy over dx? Well, dy over dx is asking us to find the derivative of y with respect to the variable x. So we can use our power rule. The derivative of x cubed with respect to x is 3x squared. Let's think about what this actually means. So let's say we have a graph of our equation y equals x cubed. Now for this graph, our independent variable is x, so that's on the horizontal axis, and our dependent variable is y. And when we talk about the slope of our curve at some point, it's the change in y over change in x. The slope of our tangent line, since our tangent line is linear and has a constant rate of change, the slope of the tangent line we can think of rise over run, or delta y over delta x, the change in y over the change in x. And this Greek letter delta is where the d comes from in the dy dx. So dy dx is the slope. And we can interpret that as the change in y over the change in x, or the change in y per unit change in x. So what I mean by that, let's say, for example, our slope is 3. Well, how do we interpret that? A slope of 3, what does that mean? What does the 3 mean? Well, if we think of 3 as a fraction, 3 over 1, that means y increases by 3 as x increases by 1. So we can think of our slope as the change in our dependent variable per unit increase in our independent variable. So here's my dependent variable here. Here's my independent variable here. And the slope is going to tell me, so once I figure out like a numerical value of a slope, that's going to be the change in my dependent variable per the unit change in my independent variable. Okay, so going back to our example, if y equals x cubed, dy dx equals 3x squared. We found the derivative with respect to x. This value, or this variable down here, is referring to our independent variable. Slope is rise over run, so the rise is the change in y, the run is the change in x in this case. So this variable in the denominator of my derivative notation is for my independent variable. Now, keeping all of that in mind, let's look at the next example. In the next example, we have the equation y equals t cubed. Well, y equals t cubed looks very similar to y equals x cubed. And the derivative of y equals x cubed was 3x squared. So you might want to say that the derivative of y equals t cubed is 3t squared. However, 3t squared is the derivative of t cubed with respect to t, not with respect to x. If I were to graph y equals t cubed, here's y equals t cubed, but when I label the axes on my graph, it's not x and y, it's t and y. So y equals t cubed, my dependent variable is y, but my independent variable is t. So when I find the slope at a certain point here, I'm not finding dy dx, I'm finding dy dt, the change in y per change in t. So the 3t squared here is not dy dx, it's dy dt. dy dt equals 3t squared. And in this problem, we're asked to find dy dx. So it seems like we have the wrong variable. T is the wrong variable. And to try and get this derivative, dy dx, the independent variable is supposed to be an x. So what can we do about this? Well, we can get dy dt. dy dt we know is 3t squared. And think about, what would you have to multiply dy over dt by to make it equal dy over dx? Well, we would want the dy to stay in the numerator. we'd want a dx to appear in the denominator, and we'd want to get rid of this dt. So I'm going to put a dt here in my numerator. So if I multiply dy over dt by dt over dx, then the dt's cancel out and leave me with dy dx, which is the derivative I'm trying to find. So dy dx in this case is equal to dy dt, which I know is 3t squared. That's the derivative of y with respect to the variable t, times dt dx. And dt dx, I don't know the value of, so I'm just going to write dt dx. So this is the answer for the second problem. If y equals x cubed, then dy dx equals 3x squared. But if y equals t cubed, then dy dx equals 3t squared times dt dx. So taking the derivative of 3t squared, or taking the derivative of t cubed, gives us 3t squared if we're taking the derivative with respect to t. But we want to change our derivative so that it's in terms of x, or with respect to x. So we multiply by dt over dx to compensate for the change in variable. Let's practice this some more. So suppose we want to find the derivative of y cubed with respect to x. So here x is the independent variable, but I'm trying to find the derivative of y cubed. That's the wrong variable. If I were taking the derivative of x cubed with respect to x, then my answer would just be 3x squared. But y cubed, y is the wrong variable. It doesn't match my independent variable. So we need to compensate for this using the chain rule. We're going to first take the derivative of y cubed with respect to y. So the derivative of y cubed is 3y squared with respect to y. But we want our derivative to be with respect to x. So now we're going to multiply that by dy over dx. Number 2, the derivative of w to the power 4 with respect to x. So let's take the derivative of w to the power 4, which would be 4w cubed, but that's the derivative with respect to w. To change that so it's with respect to x, we multiply by dw over dx. Number 3, the derivative of 6z with respect to x. The derivative of 6, z is just 6, but that's the derivative with respect to z. We want the derivative with respect to x, so we're going to multiply that by dz over dx. Number 4, the derivative of x squared plus y with respect to x. Well, the derivative of x squared. Now, x squared is the proper variable. My independent variable is an x. And so when I take the derivative of x squared, that is the proper variable. The derivative is 2x, and I don't need to adjust that. That's just it, 2x. Plus, but now when I go to find the derivative of y, this is the wrong variable if we're taking the derivative with respect to x. So I go ahead and take the derivative with respect to y. The derivative of y is 1. But then I have to multiply that by dy dx. So 1 times dy dx is just dy dx. And number 5, we want the derivative of x squared plus y squared with respect to x. So I start by finding the derivative of x squared. That's 2x. And that does match my independent variable, so I don't have to do anything special there. Plus the derivative of y squared, that's the wrong variable. So I take the derivative of y squared with respect to y, that's 2y, times dy dx, so that the derivative is with respect to x. Here we have the definition of an explicit equation. In an explicit equation, one of your variables is separated and isolated on one side of your equation. So in the first example, we have y by itself on one side of the equation. So I can say that y is explicitly defined in terms of x. Y here is a function of x. In our second example, the w is by itself on one side of the equation. So y is defined explicitly in terms of t. And in our third example, u is by itself on one side of the equation, so u is an explicit function of y. Now, explicit functions are really nice for us to work with. They're the kinds of functions that we can graph in our graphing calculator. So in your graphing calculator, you're forced to enter your equations in the form of y equals something in terms of x. So in order to do that, you have to have your equation defined explicitly. Otherwise, you can't enter it into the calculator. So what if our equation is not written in explicit form? Well, if it's not an explicit equation, then we call it an implicit equation. So an implicit equation is just one that is not explicitly defined. And we have several examples here. I've got xy equals 3x plus 2. So the x is not by itself on one side of the equation. The y is not by itself on one side of the equation, so this is an implicit equation. Now, if we wanted to, we could divide both sides of this equation by x, and that would turn it into an explicit equation. Second example, x cubed plus y cubed equals 5y. This is not an explicit equation because we don't have y by itself on one side of the equation or x by itself on one side of the equation. Even if we wanted to, we would not be able to solve this equation for y. So we cannot write this in explicit form if we want it in the form of y equals a function of x. However, we could solve this equation for x. If I subtract y cubed on both sides, I'd have x cubed equals 5y minus y cubed, and then I could take the cube root of both sides, and I'd have x equals the cube root of 5y minus y cubed. So now I've converted this into an explicit equation. But I wouldn't be able to do that for y in this example. In our third example, the square root of x plus y equals 3 is an implicit equation. X is not by itself on one side. Y is not by itself on one side. So this is an implicit equation. If I wanted to, I could convert this into an explicit equation. I could square both sides, have x plus y equals 9, and then I could subtract x, so I'd have y equals 9 minus x. Y equals 9 minus x is an explicit equation. So sometimes we do have that option. When we're working with implicit equations, we can try and solve the equation for one of the variables to turn it into explicit form. But what we're learning about today is how to work with implicit equations, how to find the derivative of these equations without having to write it in explicit form first. In this example, we're asked to find dy dx if x squared plus y squared equals 25. So we do have the option of solving this equation for y and then finding the derivative of y with respect to x. But we could also just take the derivative as is. We just have to keep in mind that if we're looking for dy dx, then x is the independent variable. That is the proper variable when we're taking our derivative. And anytime we take the derivative of a different variable than x, we have to use the chain rule to bring it back to a derivative in terms of x. So let's just start. We go left to right, term by term. The derivative of x squared is 2x. X is the proper variable, my independent variable, so I don't have to do anything special there. The derivative of x squared with respect to x is 2x. Plus the derivative of y squared with respect to x. Well, the derivative of y squared is 2y with respect to y. But if I want to turn this into a derivative with respect to x, I'm going to have to multiply by dy dx. Equals, and then the derivative of 25 is 0. So this is my derivative equation, but it's in implicit form right now. It hasn't been solved for dy dx, so we're going to do that as our next step. We want to solve it for dy dx. So I'm going to subtract 2x on both sides and then divide by 2y on both sides. And I get dy dx equals negative 2x over 2y. We can cancel out our 2's, common factor in the top and bottom of our fraction, and we get negative x over y. So dy dx in this case equals negative x over y. We're not used to seeing derivatives that have both x's and y's in them, but that's perfectly acceptable and will often happen when you're taking the derivative in implicit form. For our next example, we have a curve given by x cubed plus y cubed equals 4xy plus 1. And we're asked to find the slope of the tangent line at the point 1, 2. So the point 1, 2 is right here. And the slope of the curve at that point would be the slope of the tangent line to the curve at that point. So there's my tangent line that I've drawn. I want to find the slope of that tangent line. So this equation, x cubed plus y cubed equals 4xy plus 1, is an implicit equation. It has not been solved for y or for x. And we can see from the graph, it's not even a function, right? It fails the vertical line test. So this implicit equation is not a function. But that's okay. It still has a slope at the various points along the curve. And we can still find the slope by taking the derivative and evaluating it at a specific point. So to find a derivative, we're going to use implicit differentiation. So left to right, I'm going to take my derivative term by term of my equation here. The derivative of x cubed is 3x squared. And the graph of this equation, my independent variable is x. I know it's not labeled there, but it really should be, is x. My dependent variable is y. So I'm finding dy dx when I find the slope. I'm finding the change in y over the change in x. So we are taking our derivative with respect to x. The derivative of x cubed is 3x squared. Plus, the derivative of y cubed is 3y squared with respect to y. But since I want the derivative with respect to x, I have to multiply by dy dx. So you multiply by d, wrong variable, over d, the proper variable. Equals. Now I need the derivative of 4x times y. Well, to find the derivative of 4 times x times y, I need to use the product rule. So I'm going to group the 4 and the x together as my first factor, and then the y is my second factor, so I can do product rule. Product rule tells us to take the derivative of the first factor times the second, plus the first times the derivative of the second. So here we go with product rule. I need the derivative of the first. The derivative of 4x is 4. Then I have to multiply that by the second. The second is y. Plus the first, 4x, times the derivative of the second. So now I need to multiply by the derivative of y. The derivative of y is 1 with respect to y, but we're not taking the derivative with respect to y. We're taking the derivative with respect to x. So I have to multiply by dy dx. Or another way to think about that is the derivative of y is dy dx. Literally, we can read this as the derivative of y with respect to x. Okay, so that's the derivative of 4xy, and then our plus 1, the derivative of 1 is 0. So I don't really need to write plus 0 at the end there. This is our derivative in implicit form. So we still need to solve for dy dx. But before we move on and do that, I just want to point out, because it's a common question, people ask, why is there not a dy dx here? Like, why isn't the 4 being multiplied by dy dx? Well, in this part of the product rule, we only wanted the derivative of the first. So it was the derivative of 4x times the second. And the second was just y. So based on our product rule, we were not asked to find the derivative of y yet. We were just multiplying by y, regular old y. So that's just a y right there. But the derivative of 4x is 4, so that's where the 4 is coming from. But there is no dy dx in this term because we were not taking the derivative of a y. Okay, so in order to solve for dy dx, I have two different terms that have a dy dx in them. I want to put them on the same side of the equation. So I'm going to move the dy dx terms to the left, and anything that does not have a dy dx in it, I'm going to move to the right. So the 3y squared dy dx can stay where it is on the left side of the equation. I'm going to subtract 4x dy dx on both sides. then the 4y on the right can stay where it is, and I'm going to subtract the 3x squared on both sides. Now we're going to factor out dy dx from these two terms, leaving behind 3y squared minus 4x. And on the right, we still have 4y minus 3x squared. So dy dx equals 4y minus 3x squared over 3y squared minus 4x. That is my derivative equation, or my slope equation in general for any point along this curve. But we've been asked specifically to find the slope at this point 1, 2. So if we want the slope at 1, 2, we let x equal 1, we let y equal 2. So that would be the derivative with respect to x at the point 1, 2. So we do 4 times the y coordinate, so 4 times 2 minus 3 times the x coordinate squared over 3 times our y coordinate squared minus 4 times our x coordinate. So that's 8 minus 3 is 5, and then 4 times 3 is 12 minus 4 is 8. So the slope at that particular point is 5 over 8. And it does look indeed as though that slope is 5 over 8. It's a little bit bigger than 1/2. Next, we want to know for what values of x does this curve have a horizontal tangent. So it's the same equation we were just looking at, same graph, but now we want to know where is the tangent line going to be horizontal. So just looking at our graph, it looks like there will be a horizontal tangent right about here, right? So we get horizontal tangent right there. And then again, somewhere right around here, horizontal tangent. So if I had to guess, I would say that's about negative 0.8 or so, and then positive 1.7. But let's see if we can find a more accurate answer than that. So if the tangent line is horizontal, that means it has a slope of 0. So really I want to know, where does my slope equal 0? And I have this slope equation that we found from the last part of the question. When does this derivative equal 0? So we're going to set it equal to 0 to find a horizontal tangent. Well, our derivative is in the form of a fraction. And the only way a fraction can equal 0 is if the numerator is 0 and the denominator is not. So we're going to solve the equation 4y minus 3x squared equals 0. And then we should check to make sure our solutions don't also make the denominator 0. Because if we get 0 over 0, then that's probably not going to be a horizontal tangent. It's probably going to be a cusp, and the derivative wouldn't exist. So let's think about the solutions to this equation. 4y minus 3x squared equals 0. Well, if it were 4x minus 3x squared equals 0, we could solve that pretty easily. We could factor out an x, set each factor equal to 0, and go from there. Or we could even solve it on our calculator. But the problem here is I've got 2 variables, 2 unknowns. And when you have one equation with 2 unknowns, you can't solve it. So when you have an equation with 2 unknowns, you need a second equation written with your 2 variables so that you can solve that system of equations. Do we have another equation that relates x and y? Well, we have our original equation up here. So I've got x cubed plus y cubed equals 4xy plus 1, and I've got 4y minus 3x squared equals 0. And at our point of tangency that we're looking for, we know that the slope of the tangent line is going to be 0, and that the tangent line intersects the curve. So it makes sense to try and solve this system of equations. Now, in order to solve our system, we're going to use substitution. So you choose one of your equations. It doesn't matter which one, this one or the other one. You pick one of your equations and solve for one of your variables. Well, in the original equation, it looks like it's going to be pretty difficult to try and solve for x or to try and solve for y. So let's go with our new equation and solve it for y. So I'm going to get 4y equals 3x squared, or y equals 3x squared over 4. So divide both sides by 4. We get y equals 3x squared over 4. So now I can take this value that's equal to y is 3x squared over 4. I can take that and I can substitute it into the other equation in place of the y. So my equation is x cubed plus y cubed, but I'm going to substitute 3x squared over 4 in for y. So 3x squared over 4 cubed equals 4 times x times y, but I'm going to substitute 3x squared over 4 in for y, and then plus 1. So that's my new equation, and this new equation only has one variable in it, so we can solve it. Okay, we're going to solve this on the calculator graphically. So in y1, we're going to enter the left-hand side, x cubed plus 3x squared over 4 cubed. And then in y2, we're going to enter the right-hand side of our equation. So the 4x times 3x squared over 4 plus 1. And then we're going to look for a point of intersection. Okay, so solving that equation, we get x equals negative 0.77 or x equals 1.732. And that is where we estimated our solutions to be. Negative 0.77 would be this x value here, and then the 1.732 is this x value here. Now the one thing I didn't do was check to make sure for these values of x, the denominator is not 0. However, since I'm looking at the graph and I can see visually that these are definitely my two solutions, I really don't have to bother checking. But normally what we would do is substitute these values back into the denominator and make sure that the denominator is not also 0 at these points. Next, still working with the same equation, we want to find where does the curve have a vertical tangent. So just looking at our graph, it looks like we have a vertical tangent right here, and then right about here. So our solution should be about maybe 0.4, positive 0.4, and then 2.2 or 2.3, somewhere around there. So a vertical tangent means the tangent line is vertical, and vertical lines do not have slopes of 0. Vertical lines have undefined slopes. So if our slope is undefined, that means our derivative has to be undefined. So how are we going to find the places where our derivative is undefined? Well, our derivative is set up as a fraction. So this is going to be undefined when the denominator is 0 and the numerator is not. Again, we don't want to get 0 over 0. We want to get 0 only in the denominator. So we want to know, where does 3y squared minus 4x equal 0? Again, this equation has two unknowns, so we can't solve just from this. We have to use a system of equations. So we use our original equation that relates x and y, and we use this new equation setting our denominator equal to 0. And we're going to solve that system. So this time, to solve the system, I'm going to take this second equation and solve it for x. And I get x equals 3y squared over 4. I'm going to take that x value and substitute it in for x in my other equation. That's how we solve a system using substitution. So now I'm going to have x cubed, and x is 3y squared over 4. So 3y squared over 4 cubed plus y cubed equals 4 times x, and x is 3y squared over 4, times y plus 1. Now this should look somewhat familiar. because we just solved an equation like this. It was almost identical. In fact, the only difference in the other equation that we solved was that there were x's instead of y's. Other than that, it was an identical equation. So when we solve this, we're going to get the same solution. It's just going to be the variable y instead of the variable x. So we're still going to get as our solution y equals negative 0.77 and y equals 1.732. But we're actually not interested in the y values. We were asked in the question for what values of x will the curve have vertical tangents. But since we know our y values, we can substitute them back into one of the equations in our system to get the x values. So you could use the original equation, but that one's pretty complicated. It would be easier to use this equation right here, which tells us x is just y squared times 3/4. So x equals y squared, negative 0.77 squared, times 3/4. Or here, x equals the 1.732 squared times 3/4. Okay, so we get x approximately 0.444 and x approximately 2.25. Given the curve y squared plus 2y equals 2x plus 1, find d squared y over dx squared. So let's talk about this notation for a moment. This notation means the second derivative. It doesn't mean that we're squaring anything. We're actually not going to square anything. We're finding the second derivative. So why does that notation look so funky? Well, we're using Leibniz notation. And in Leibniz notation, the first derivative is written like so: dy over dx, which really means the derivative of y with respect to x, which you'll also see sometimes written like this: d over dx of y. This is our first derivative. Okay, we want to take the derivative of that. So if I'm sticking with Leibniz notation and I want to take the derivative of dy dx, then what I'm doing is taking the derivative of dy dx with respect to x. And if I just kind of scoot this out to the side, then it looks like d over dx times dy over dx. And then the d times the y is where that d squared y comes from in the notation. And in the bottom, we have dx times dx, which is dx squared. And mathematically, yes, we should have like parentheses around that squared, but for whatever reason, people just drop the parentheses and write the square on the outside like so. So all this means right here is find the second derivative. And the second derivative is just the derivative of the first derivative. So let's find our second derivative. And to start, we're going to find our first derivative. Now this is an implicit equation, so we could try and solve it for y if we wanted to, but it's not necessary to do that. It's going to be far simpler to just go ahead and use implicit differentiation. So term by term, I find my derivative. The derivative of y squared is 2y, but that's with respect to y, not x. I want to find the derivative with respect to x. So I multiply that by dy dx. Plus, the derivative of 2y is 2, but again, that's with respect to y. To make it a derivative with respect to x, we have to multiply by dy dx. Equals, the derivative of 2x is 2, and that is with respect to x. That's the proper variable, so I'm good to go there. The derivative of 1 is 0, so I don't need to write that. Now, notice every term in this equation is multiplied by 2. So I'm going to go ahead and simplify this by just dividing both sides of the equation by 2. And then I have y dy dx plus dy dx equals 1. I can factor out dy dx, leaving behind y plus 1. And then dy dx equals 1 over y plus 1. That's my first derivative. So let's take the derivative of that equation. On the left, I want the derivative of dy dx. The derivative of dy dx is d squared y over dx squared, my second derivative. Equals. Now on the right, I have to take the derivative of 1 over y plus 1. There's a couple ways we can do this. We can use the quotient rule, or we can write 1 over y plus 1 as y plus 1 to the power negative 1 and use the power rule combined with the chain rule. I think it'll be easier to just go ahead and do quotient rule, so that's what I'm going to choose. For quotient rule, I take the derivative of the top. The top is just 1. The derivative 1 is 0. So derivative of the top multiplied by the bottom minus the top multiplied by the derivative of the bottom. The derivative of the bottom, I need to take the derivative of y plus 1. Well, the derivative of y is 1 dy dx plus the derivative of 1 is 0. Okay. All over bottom squared. So this is 0 times y plus 1 is 0. So that completely drops out of our equation. So I have negative dy dx. We're not going to leave a dy dx in our answer. We're not going to leave dy dx in our answer. We know what dy dx is equal to. We found it over here. So we're going to substitute that in for our dy dx. 1 over y plus 1 equals dy dx. So negative 1 over y plus 1. I'm substituting that in for the dy dx over y plus 1 squared. And that simplifies to negative 1 over y plus 1 cubed. Let's do another second derivative example. Here our equation is x squared plus y squared equals 1. We want to find the second derivative. So we start by finding our first derivative. Derivative of x squared, 2x, plus derivative of y squared, 2y dy dx, equals the derivative of 1 is 0. Now let's solve this for dy dx. I can divide both sides of the equation by 2 to make this a little bit simpler. So x plus y dy dx equals 0. And then dy dx equals negative x over y. That's my first derivative right there. Now the second derivative, I'm going to take the derivative of this equation. On the left-hand side, the derivative of dy dx is the second derivative, d squared y over dx squared. On the right, the derivative of negative x over y. I'm going to use the constant multiple rule and the quotient rule to find this derivative. So the negative 1 I'm going to keep outside and then multiply that by the derivative of x over y. So using quotient rule, the derivative of the top is 1 times the bottom minus the top times the derivative of the bottom, and the derivative of y is 1 times dy dx, all over the bottom squared. Now I can distribute my negative, so I have negative y plus x times dy dx, and I'm not going to keep dy dx in my answer. I'm going to substitute negative x over y in for dy dx, because that's what my first derivative is equal to, over y squared. I have a complex fraction, that means a fraction inside of a fraction, so we multiply by the least common denominator of our inside fraction over itself. So we multiply like that, and then I have to distribute this, so the y times the negative y is negative y squared. The y times the x times the negative x over y, the y's cancel here and just give me negative x squared over, and then I have the y times the y squared, which is y cubed. So that is my second derivative. Our next example, consider the curve defined by 2y cubed plus 6x squared y minus 12x squared plus 6y equals 1. Show that dy dx equals 4x minus 2xy over x squared plus y squared plus 1. So we're going to take the derivative of our equation with respect to x. The derivative of 2y cubed is 6y squared dy dx. Plus, now I need the derivative of 6x squared times y. So we have to use the product rule. I'm going to group 6x squared as my first factor and then y as my second factor. So product rule tells us to take the derivative of the first, that's 12x, multiply it by the second, plus the first, 6x squared, times the derivative of the second. The derivative of y is 1 dy dx. Minus the derivative of 12x squared, that's 24x, plus the derivative of 6y, that's 6 dy dx, equals the derivative of 1 is 0. So now let's factor out dy dx from the terms that contain dy dx. So we get dy over dx times 6y squared plus 6x squared plus 6 equals, and then the terms that did not have dy dx, I'm going to move over to the right-hand side. So I'm adding 24x to both sides, and then I'm subtracting 12xy on both sides. And now to solve for dy dx, I'm going to divide both sides by 6y squared plus 6x squared plus 6. So we get dy dx equals 24x minus 12xy over 6y squared plus 6x squared plus 6. Now I can factor a 6 out of the top and a 6 out of the bottom, and then those 6's will cancel out. So factoring a 6 out of the top leaves behind 4x minus, and then taking a 6 out of 12xy just leaves 2xy. On the bottom, factor out a 6, we're left with y squared plus x squared plus 1. Our 6's cancel, and then we have our answer in the form that we were trying to get. So we're trying to show that our derivative was 4x minus 2xy over x squared plus y squared plus 1. For the next part, we want to write an equation for each horizontal tangent line to the curve. So the horizontal tangent line means the slope is going to be 0. And my slope will be 0 when the numerator is 0. So whenever 4x minus 2xy equals 0. Now the last time we had a problem like this, we needed to solve a system of equations. But here it's a little bit different because I noticed that I can factor out a 2x here, leaving me with 2 minus y equals 0. And since this is in factored form and one side is equal to 0, I can now set each factor equal to 0. So I get 2x equals 0, which means x equals 0, or 2 minus y equals 0, which means y equals 2. So I need to know the equation of the horizontal tangent line. So it looks like it's probably y equals 2 is one of them. And then x equals 0 is just the x coordinate of the point of tangency where the slope is 0. So I still need to figure out the y coordinate. So if I know x is 0, how do I find y? Well, that's when I have to go back to my original equation up here. And if x is 0, I substitute that in for x. I get 2y cubed plus 0 minus 0 plus 6y equals 1. Now this isn't something we can factor and solve by hand. So we're going to go to the calculator and solve this equation. We get y equals 0.165. So it seems like we have two solutions, y equals 2 and y equals 0.165. But we need to check these solutions. So when we substitute the y equals 2 back into our original equation to try and solve for the corresponding x value, watch what's going to happen. So if y is 2, I'm substituting that in for y into this original equation. I get 2 times 2 cubed is 8, so 2 times 8, plus, then I have y is 2, so I have 12x squared minus 12x squared plus 6 times y, and y is 2, equals 1. So I get 16, this is 0, plus 12 equals 1. Well, we know that's not true. 28 does not equal 1. So this is actually a false solution. It doesn't satisfy our equation. It satisfies the derivative equation, but it doesn't satisfy the original equation. So the only solution to this problem is the y equals 0.165. Number 3, the line through the origin with slope -1 is tangent to the curve at point P. Find the x and y coordinates of point P. So this line passes through the origin. It has a slope of -1, and it's tangent to the curve at point P. Well, we can figure out the equation of this tangent line. If it has a slope of -1 and it passes through the origin, then the equation of that tangent line is just y equals -x. So there's the equation of our tangent line. This line is tangent to our curve at point P. So it intersects our curve at point P. We also have the fact that the slope is -1. So the slope of our curve is -1 because the slope of the tangent line and the slope of the curve are the same at the point of tangency. So we know our derivative is equal to -1, and our derivative is a fraction. The only time a fraction is going to equal -1 is when the numerator and the denominator are opposites of one another. So now I know 4x minus 2xy equals the opposite of x squared plus y squared plus 1. I have a system of equations here that I can solve. So I already know that y equals -x. I can substitute that into this other equation in place of y. So that would give me 4x minus 2 times x times -x, so plus 2x squared, equals -x squared, I'm distributing this negative here as I go, minus y squared. But y squared equals x squared, so it'll be minus x squared, and then the plus 1, I'm distributing the negative, so I get minus 1. Okay, so now the -x squared is -2x squared. If we add that to both sides, then over here we get 4x squared. And I have a plus of 4x, and if I add the 1 over, I have plus 1 equals 0. And we can factor that. We get 2x and 2x, 1 and 1. And I need a 4x in the middle, so that's going to be plus plus equals 0. So x equals -1/2. X equals -1/2, and I can go back to this equation that relates x and y to figure out the corresponding y value. So if x is -1/2, then y is the opposite of -1/2, or just +1/2. So I have x equals -1/2, y equals +1/2. For our last problem, we're going to use implicit differentiation to find dy dx and determine the equation of the tangent line at the given point. So for part A, to find the equation of the tangent line, we're going to need to know the slope of the curve at the point -3, 3. So we start by finding our derivative. The derivative of x cubed is 3x squared, minus the derivative of y cubed is 3y squared times dy dx, equals the derivative of 6 times x times y. I'm going to use product rule, treating 6x as my first factor, y as my second factor. So the derivative of the first is 6 times the second plus the first times the derivative of the second. The derivative of y is 1 times dy dx. So there's my derivative equation. I'm going to solve this for dy dx. So I'm going to group my dy dx terms together. Subtract the 6x dy dx. subtract the 3x squared, factor out the dy dx, and then solve for dy dx. So 6y minus 3x squared over negative 3y squared minus 6x. Now we want to find the value of dy dx at the point negative 3 comma 3. So 6 times the y value, 6 times 3 is 18, minus 3 times x squared. X squared is 9. 3 times 9 is 27. So 18 minus 27 over negative 3 times y squared. Y squared is 9, so negative 3 times 9 is negative 27, minus 6 times x. So minus 6 times minus 3 is plus 18. So this is negative 9 over negative 9, or 1. So the slope of our tangent line is 1, and the point of tangency is negative 3, 3. So my equation will be y minus 3 equals 1 times x minus negative 3, or x plus 3. Now part B, we want to find the derivative of our equation. The derivative of sine of y is cosine of y times dy dx, plus the derivative of y is 1 times dy dx, equals derivative of x cubed is 3x squared, plus derivative of x is 1. Factoring out dy dx leaves cosine y plus 1, and we'll divide both sides of the equation by the cosine y plus 1, leaving dy dx equals 3x squared plus 1 over cosine of y plus 1. And we want to find dy dx at the point 0, 0. So I'm going to substitute in 0 for x and 0 for y. 3 times 0 squared plus 1 is 1. The cosine of 0 plus 1 is 2. So my slope is 1/2. And my equation is passing through the point 0, 0. So it'd be y minus 0 equals 1/2 times x minus 0, or just y equals 1/2 x.